Hello everyone, my name is Keywoong from Inha University. Today I'm going to introduce about my paper, Transformer Networks for Trajectory Classification. Now, various studies using trajectory are currently ongoing, and among them, trajectory classification is one of the areas currently being actively studied. With the recent success of deep learning, it started to be applied in this field. Since trajectory data is time series sequence data, RNN series models are widely used in trajectory classification analysis, for example, RNN, LSTM, and GRU. Trajectory classification is one of the widely studied problems on trajectory pattern mining over the years. There are three basic examples of trajectory classification. First one is determining the transportation mode of the moving object. Second is determining what one's next stopping point. And the third is identifying who is the user of a trajectory, TUA problem, trajectory user linking problem. In these examples, RNN, LSTM, and GRU are frequently used. Sequence-to-sequence models are representative examples of RNN. These models have encoder and decoder structures in which the encoder receives the input values and compresses them into one vector representation, which is called context vector. However, these models have a disadvantage that if the length of the input sequence is too long, a bottleneck problem occurs in the process of compressing it with the context vector, and it results in loss of information of the input sequence. To solve this problem, Google proposed a transformer model using attention mechanism. In this paper, we propose trajectory classification using transformers attention mechanism. And I'm gonna tell you about the related work of transformer networks for trajectory prediction. In this paper, it conducted a comparative experiment between LSTM and transformer using trajectory datasets. Transformer use attention mechanism, and with this characteristic, transformer performs better in trajectory prediction than LSTM. Though the above examples, it can be seen that transformer has performed sufficiently well in the field of trajectory prediction. We judged that this transformer could be used in the field of trajectory classification, which is currently being applied in various ways. To find the suitable model for trajectory classification, we used the Mnist stroke sequence data and put them into RNN, LSTM, and transformer and compared their accuracies. Mnist sequence data have 4 dimensions. The first and second columns, which are delta x and delta y, represent the horizontal and vertical movements. The third column, which is end of stroke EOS, is 1 when the point is the last point of the stroke. In other words, the pen deviates from the paper after the point. The fourth column, end of digits EOD, is 1 for the last point of the entire sequence. We use Mnist stroke sequence data for sequence classification. We judge that this dataset is sufficient as a dataset for trajectory classification in that it has a starting point and a last point, and it can express the process of writing as a trajectory. Next is the setting of our experiments. In RNN and LSTM, the input shape is like this, and time step is 118. The number of cells is 32, and the number of layers is 4. In transformer, the original transformer network encoder will be used, and the input shape is like this, and the dimension of model is 512, and the number of head is 4, and the number of layers is 4. The epoch of experiment is 150 and the optimization function used in the backpropagation process is Adam optimizer. The learning rate is 10 to the minus 4 and the batch size is 64. The result of the experiment is like this. We expect transformer to perform much better than RNN or LSTM. The simple RNN model achieved the accuracy of 0.88 and 0.88 and 0.8924 in train data, validation data, and test data. The LSTM model, which is currently achieved used in trajectory analysis fields, achieved accuracy of 0.9443, 0.9419, and 0.9444. And transformer model we proposed achieved accuracy of 0.9247, 0.9312, and 0.9393 in train data, validation data, and test data in turn. In conclusion, we assume that transformer networks using attention mechanism will perform better than RNN LSTM. Although there was no remarkable difference between transformer and other models, the novelty of our approach, classifying trajectories with transformers, is shown by the fact that there has been no previous study. In addition, it is expected that there will be a distinct performance from LSTM when learning a long trajectory sequence dataset. Thank you for listening to my presentation.